Okay, so essentially we're dealing with the analytical solution of the unsimplified incompressible Navier-Stokes equations for arbitrary catchy data being initial conditions and boundary conditions of the nonlinear PDE. This clicker is not working. Okay, I'm going to go press the space bar every time. They're the holy grail of continuum fluid mechanics. There are a coupled system of PDEs that control the motion of viscous fluids. Exact solutions are only known in special cases. Practical engineering use requires CFD methods, which burns billions on slow algorithms because they're the best we have. Or it could be that we need to discover more math. But the main point here is that it's been 200 years since we've known about them. So we're going to do 9 basic steps to get to my own proprietary method to solve the equations analytically as opposed to numerically, meaning we won't have expensive iterative approximations. We're going to have a hard-sided mathematical formula that describes fluid turbulence. Big claim. Here's the big evidence. Here's the monster. Okay, so we have an advective term for turbulent flow. We have a viscous term for laminar flow, depending on which one dominates. The pressure term non-linearly loops back with velocity, and that's why it's hard. The forcing term is where gravity goes and everything else, magnetism, whatever you want. Continuity equation conserves mass. This is a liquid, so we're having zero divergence on the velocity field. First thing we do is separate the velocity field into 2 things. How much time do we have?
1 minute.
What?
We're at a minute 30.
I'm at a minute 30? Or I have a minute 30.
No, you are at a minute 30.
Thanks so much. So irrotational and rotational flow, those get split up right there by a sum. That is the Helmholtz decomposition that is standard in the literature. Inverting that requires a lot of vector calc and a lot of surface integrals and volume integrals. That is the Lie ray projection, which is where you turn the Helmholtz decomposition inside out. If I want to find the irrotational and rotational flow in terms of velocity, then full velocity, then that's what I have to do. And that's going to be very important for boundary conditions later on. First thing we do is we use standard potential flow theory for the irrotational velocity. Going through all the derivations, what essentially you have to know is that the irrotational flow is the gradient of a solution to the Laplace equation in a scalar. That is understood to be the most general formula that covers the whole solution space of an irrotational Navier-Stokes velocity field. To tackle boundary conditions, we use the irrotational Lie ray projection, and we go ahead and we're going to have to invert the gradient, which is only possible in a simply connected domain, which basically means the fluid is flowing around or through, doesn't have any holes in it, and it's one piece of mass. So if you want, if it's not that case, then it's going to get more complicated up here, and it's going to carry down into there. But for now, we're going to go and assume simply connected topology. Here's the citation if you want. Polyanin and Zaitsev have written compendiums of this stuff like the world has never seen. Next thing we're going to do is rotational flow. We have an identity in vector calculus, this thing right here. This essentially says if I take the curl of the curl and I enforce incompressibility, making this 0, then I'm going to end up with just a negative Laplacian of the velocity field, which is the diffusion rate of velocity. So basically, the vorticity's vorticity equals the diffusion according to the negative, which is pretty cool. So when we go ahead and take the curl of the curl, we're going to have rotational flow regardless because irrotational flow, by definition, has no curl. So we're going to go to rotational flow. Now this is a 4th order derivative here, and that's complicated, so we're going to go ahead and factor the Laplacian operator because it is a linear differential operator and is therefore subject to factorization. We're going to go ahead and then solve for the entire left-hand side. This right here, this whole thing, is the unknown of a Poisson equation, which is where you have the Laplacian of the unknown equaling a forcing term. This is given. Now what we end up with is we have to have our boundary conditions not just in V rotational, but in this whole expression. That's why the boundary integral term is so huge. So we've effectively replaced the pressure, because the curl of a gradient of anything is 0. We can go ahead and replace that with a giant nonlinear boundary integral term in our known information, which is pretty cool. So we've gotten rid of pressure. Now we're going to go ahead and go to a modified Cole-Hopf transformation. Now Cole-Hopf is interesting because that's essentially the Cole-Hopf transformation takes a stripped down version of the Navier-Stokes equation and turns it into a heat equation, and we already know how to solve a heat equation, so we can recover that simplified Navier-Stokes solution very easily. Now here's the thing. That's not general enough. So we're going to go ahead and do a 3-dimensional general Cole-Hopf transformation. What that basically means is if we have heat equations and heat equation solutions, which we have, then we're going to go ahead and find what theta functions, what lift functions we need to take these heat equation cores and basically turn them, map them into a Navier-Stokes solution for rotational flow. So we can solve the heat equation fine. What we don't have is the theta functions. And when we solve for those, we're looking for an OD. We have in a system of ODEs, not PDEs, ordinary differential equations, one variable, and we have these phi functions basically being the heat equation cores, which you already know. So we can go ahead and treat these as as we can go ahead and treat those as the independent variables of these ODEs. So we're mapping from theta onto the. We're mapping from the value set of these things at every xyzt onto the value set of these things. So we're not really worrying about xyzt. They're hidden inside the machinery. We got the ghost in the machine. We got phi, which we know, and we got theta, which we don't know. We're solving for theta as a set of ODEs. So we're going to go ahead and recognize the fact that if we're assuming that phi is a heat equation, then we're going to go ahead and look at the terms corresponding to heat equation, namely the time derivative and the Laplacian, and we're going to go ahead and see that they cancel, because the whole point of a heat equation is to equate a time derivative and a Laplacian, so naturally the difference equals 0. So those zero out, those cancel, and we got a much more simplified thing here. In the B functions here cover those giant boundary condition terms. We're going to go ahead and compress things into abbreviations because we're running out of time. We have slides. So we're going to go ahead and spaghettify the nonlinear terms like a black hole. So we're going to go ahead and solve these as ODEs, and that gives us a complementary solution for the unbounded Clay Mathematics Institute Millennium problem, which is where you have an ocean infinitely wide and infinitely deep, no boundary. Scary as that sounds to a lot of people. And we have the particular solution for a bounded flow, because that has the boundary term here. This has no boundary term. This just has the other stuff. So these constants are arbitrary, and we can go ahead and mark this one 0 and this one 0, and we can go ahead and cover a bounded flow. We only have time to go over the bounded flow today. This is what we end up getting. Now we have U, V, and W. We have the velocity components. We also have the full velocity field down here. So we've basically reduced this to an algebraic system. We've taken the differentiability, we're taking the differential equationness out of it. And now we end up with, that kind of went a bit wonky there. Sorry about that. A bit of turbulence on my end. So essentially, we're going to go ahead and observe. We have quadratic, we have a quadratic, and we have a quadratic down here. And everything else is a linear term. So basically that means we have a triquadratic system. We've effectively taken the nonlinear term of Navier-Stokes, we've ripped it down to a triquadratic system, and it's shoveling heat equation core gradients around like they're coal going into a furnace. So you can see where turbulence kind of comes from here. This is the engine of turbulence, right, where you're looking at. Now, mapping the heat equation cores to the velocity field requires this and that to be basically the same. And these definitions to be assumed. We're going to go ahead and tear this. We're going to make the substitution and tear this down to a biquadratic system, because 2 is easier than 3. Olga Lattes and Skaya found that out the hard way in 1958. So we're also going to abbreviate these heat equation core gradients. And again, these are not again. I'm first time introducing this really. We have heat equation core gradient component number 1, component number 2, component number 3. The reason I'm writing it that way is to make this coordinate agnostic. It's going to be rectangular, cylindrical, and spherical all rolled into one. So we got that. So we're going to go ahead and solve for alpha and beta. Now substituting the first biquadratic into the second biquadratic equals a quartic whose coefficients are so ridiculously huge, I have to do 2 layers of abbreviation to write them down here for you. And solving that quartic is possible per the Abel-Ruffini theorem. It says that any polynomial with a degree lower than 5 is possible to solve analytically in closed form. So you now have a quartic solution. You now have beta, but it's kind of complicated. So I have to make a bunch more abbreviations here. Now, substituting that back into the other equation means that knowledge of alpha follows. Now, what we have now is we have U, V, and W, because we can go ahead and invert the definitions of alpha and beta, which we know from the quartics, to get the velocity formulas. So we're going to go and push this into vector notation, and this is what we end up getting. So we're going to go ahead and observe this. We have the heat equation cores, it's nice, but their boundary conditions and initial conditions are in the heat equation. They're not in Navier-Stokes. We have to turn that heat into velocity. So we're going to go ahead and we're going to go back to the formula where we chose the particular solution instead of the complementary solution of the ODE for the lift function. We're going to go ahead and solve not for the velocity, we're going to solve for the heat equation cores, and we're going to go ahead and evaluate that on the boundary and evaluate that at the initial, and we're going to plug that into the heat equation, and we're going to finally get our velocity field. So we're going to use the method of characteristics, and because we're running out of time, as always, we got basically this. This is a standard result. We're going to go ahead and basically what this is we're going to go ahead and knock out the term in the heat equation cores that is not being differentiated by using an exponential. And then we're going to go ahead and basically fire off curves through the domain and watch how they hit the other side of the domain and then make sure they conserve energy, and whatever that constraint would be is what gives us these formulas here. That's basically a 30,000 foot view of method of characteristics, but it's a very standard method in PDE theory, and any PDE researcher worth its salt should be able to replicate this. Now we're going to go ahead and take the heat equation data, turn them into mass flow data. We're going to go ahead and plug those formulas we just saw into the heat equation cores. We're also going to use the rotational linear projection to make sure that we have boundary conditions in full velocity, and initial conditions also, instead of just the rotational velocity. So we now have our full specification of phi in terms of velocity. If you have velocity initial boundary conditions, you can find phi closed form for any domain that is simply connected, and if it's multiply connected, make it a wee bit more complicated, and you've got it made. So next thing to do is recover the pressure field. All you have to do is take the divergence of the momentum equations from the beginning without even solving them, and the divergence of a gradient is a Laplacian, and when you have a Laplacian of your unknown equal to a known thing, what do you got? A Poisson equation. We can already solve that. That's a known solution. So all we have to know is velocity, and we now have the divergence of that giant material derivative. But it's something we already know because we just found all the ingredients for velocity. So when you have velocity, you just plug it in and find pressure. Now this term may or may not be necessary. That's what I need to figure out when peer review comes. That's where my knowledge ends and their knowledge transcends mine. I'm going to have to ask the reviewer when this manuscript goes in for peer review whether this term is intrinsically necessary to the formulation of the solution space. Now here's the big solution. 200 years, and here it is. So here's the velocity field, and we got the heat equation cores coming out of our quadratic system, and I've written that generally because I can't write a giant quartic in this little tiny space. We now have the boundary condition terms specified in full. We have those specified with the linear projections, so we can go ahead and get the boundary conditions straight. We now have pressure, and we have heat equation cores up here, and we have their characteristic boundary condition reconciliation formulas. Basically, these feed into the heat equation cores for the boundary conditions and initial conditions. Those go into the quartic system, and those go into the velocity field. And then you had the boundary conditions basically being shorthand for this. So basically, all these formulas get plugged into the velocity field and pressure field, and you end up with a giant formula that is miles and miles long. So the quartic roots, they collapse mathematically to quadratic roots in 2D and cease to exist at all in 1D, shedding light on Lottes and Sky's inequality being valid here. When all four roots of any quartic equation coincide, they all equal 0. And when you have 0 quartic roots, you have 0 rotational flow, because the only time they arise is rotational flow, you have 0 turbulence. So if you have less root multiplicity, you have more complexity in the lift functions and more nonlinear chaos. So the mathematical essence of turbulence could very well be the quartic root multiplicity class, where the edge of fluid chaos, the laminar turbulent transition, may find its essence in the quartic discriminant, which is many terms long, but will give you a constraint on the heat equation core gradients that will show you exactly what initial boundary conditions will produce a laminar turbulent transition at a specified Reynolds number, inertia to viscosity ratio. The clay Millennium problem is an edge case using the complementary system of lift ODEs. As I said, it's exponential, so you're going to end up with your unknown inside and outside of an exponential. You're going to end up with a trivariate Lambert W function. For that, you're going to read my manuscript, and I can't unpack that because I literally had to discover that and prove it existed by the implicit function theorem. That is literally the latter 1/3 of my manuscript, and you can look that up on Orca, you can look that up on Zenodo, ResearchGate, whatever. It's easy to find. So basically, till peer review and more time to go more in depth on everything, QED. That's basically the end of the proof. Do you have any questions and answers? Questions?
This is awesome.
Thanks.
Is there any simulation of this, or mathematical proof?
The mathematical proof is in the manuscript, and the simulation is a work in progress currently.
That's awesome. Nice job.
So yeah, if you want the rigorous mathematical statements with the lemmas and the theorems and the claims and all that jazz, the manuscript has all of those things all structured out.
Yeah. Thank you so much.
It's a 52-page brick, but I have faith in you as University of Tampa students that love to read things. You can fight your way through it.
Yeah.
Just send me a message anytime if you get confused. I'll help you out.
Okay.
Really interesting presentation, but I have just one question. So what's the current limitation of his solution?
The current limitation of the solution is incompressibility. And as stated here, simply connected domain. It can be generalized very well to a multiply connected domain. And as far as incompressibility being generalized, that's gonna require some effort on my part to figure out what that's going to mean for the quartics. It might go to octic, So or even worse. But basically, the strictest limitation is incompressibility.
Okay.
The flow must be incompressible. It must be a Newtonian liquid.
Thank you so much.